In this video, we'll be exploring powers with integral exponents. In Math 9, students first learn about exponents, and now in grade 10, their understanding is extended to include negative exponents. Integral exponents, especially negative exponents, can be helpful in many real-world problems. For example, looking back in time when something grows, like a plant, bacteria population, or investment. Very small things, like molecules, are measured using scientific notation with negative exponents. And some things, like the amount of light as one descends deeper into water, can be modeled using negative exponents. Let's begin by reviewing positive exponents. One meaning of exponents is to represent repeated multiplication. We can represent this repeated multiplication using what is called exponential form. The 3 represents the base, and the 5 represents what is called an exponent. When a number, the base, is raised to an exponent, it is called a power. And we read this power by saying 3 to the power of 5. But what if the exponent is a negative integer? Let's first use a pattern to figure out what a negative exponent could mean. 2 to the power 3 means 2 times 2 times 2, which is 8. With the same reasoning, 2 to the power 2 is 4, and 2 to the power of 1 is 2. Notice that each time we decrease the exponent by 1 corresponds to dividing the answer by 2, which also means cutting it in half. So if we continue the pattern, 2 to the power 0 must be half of 2, which is 1. What about the next ones? How does this pattern continue? Continuing to take half, 2 to the power of negative 1 would be half of 1, which is 1/2. 2 to the power of negative 2 would be half of a half, which is 1/4. To see this a similar way, let's compare 2 to the power of positive 2 to 2 to the power of negative 2. We can express 2 to the power of 2 not just as 2 times 2, but also 1 times that. We can express 2 to the power of negative 2 in a similar way, but this time by dividing by 2 twice. So just as positive and negative integers are opposite, so are the operations that they define. Comparing 4 to 1 over 4, each is said to be the reciprocal of the other. With this in mind, what do you think the reciprocal of each of these numbers is? As a first step, we can make sure each number is written as a fraction. Then, because reciprocal means to do the opposite or inverse in terms of multiplying and dividing, to take the reciprocal, we reverse the position of each number. For 3 over 1, we can just write 3. In order to explore a more conceptual way to understand negative exponents, we first need to see what happens when we divide powers. This is something your child learned in Math 9. First, we express the powers as repeated multiplication. Notice we have a 3 times 3 in both the numerator and denominator, and this is equivalent to multiplying by 1. So we can remove this from our product. So our quotient is equal to 3 to the power of 3. Recall that by dividing by 3 to the power of 2, we were able to remove 2 factors of 3. So it is by subtracting the exponents that we get our answer of 3 to the power of 3. In general, to divide powers with the same base, we subtract the exponents. Because we cannot divide by 0, we cannot have a base of 0. This is an example of what's called an exponent law, and specifically, it's called the law for dividing powers. Using this law, we can look at something like 3 to the power of negative 3 and imagine how that negative 3 came from subtracting two exponents. This would then correspond to dividing by 2 powers of 3. So let's think about possible values for the green and purple squares. Whatever numbers we choose, we need to have a difference of negative 3. So these could be 0 and 3, 1 and 4, 2 and 5, and so on. This means our powers of 3 should also have these exponents. So let's expand each power. And notice that the 3 times 3 in both the numerator and denominator means that those factors are equivalent to multiplying by 1. So our answer is 1 over 3 to the power of 3. And generally, a negative exponent means to do the opposite or inverse operations. In other words, we take the reciprocal. And so another general expression we can state is that a over b to a negative exponent is its reciprocal to the power of the positive exponent. There are several other exponent laws that your child learned in Math 9 that are going to be useful in grade 10. We've already seen the law for dividing powers, and that anything to the power of 0 is 1. Just as we subtract exponents when dividing powers, we add them when multiplying. Finally, when there is a power of a power, we multiply the exponents. Let's apply what we have learned about powers with integral exponents to solve some problems. In this first task, we are asked to write each expression using positive exponents. The exponent laws are helpful to figure these out. Which exponent laws can help you solve each problem? For the first one, it helps to consider the number and the variable separately. 2/3 to the negative 3 means we can take its reciprocal and write it to the power of positive 3. For the variable power, we can multiply the exponents. Evaluating each, we get 27/8 times c to the power of 12, which we can write as 27 c to the 12th over 8. For the next one, it is helpful to simplify what is within the square brackets first. This is a product of powers, so we add the exponents, and this sum is negative 6. Now we have a power to a power, so we multiply the exponents. The final answer is m to the power of 18. For the final one, let's look at the division of powers, so we subtract the exponents. This gives us b to the 7th to the 3rd. This is a power of a power, so we multiply the exponents, and our final answer is b to the power of 21. Our next problem is to evaluate an expression, given the values of each variable. How would you approach solving this problem? Give it a try. One may wish to substitute first, but that creates a lot of unnecessary work. It is much more efficient to simplify the expression before substituting in the values. We are dividing powers, so we should subtract the exponents. This gives us c to the negative 2 times d to the positive 4. Doing the inverse to c to the negative 2 makes it dividing by c to the positive 2. Now we are ready to substitute. Our final answer is 16/9. Our final problem considers the intensity of light underwater as a diver dives deeper. As the diver dives deeper, the light intensity decreases. We can model this decrease by stating the percent intensity is equal to 2 to the power of negative k, where k is the depth in 20-meter increments. What percent is the light intensity when the diver reaches a depth of 80 meters? K is the number of 20-meter increments, so for 80 meters, K must be equal to 4. 2 to the negative 4 is equivalent to 1 over 2 to the positive 4, or 1 over 16. If we divide 1 by 16 using a calculator, we get 0.0625, which is equivalent to 6.25%. This video addresses several learning standards in the Foundations of Mathematics and Pre-Calculus 10 curriculum. Throughout the video, we made connections between powers and the other operations. The content standard we focused on was operations on powers with integral exponents. As your child learns about powers with integral exponents in their classroom, several curricular competencies may emerge. For example, we analyzed and reasoned to be able to make sense of what negative exponents could mean. We used negative exponents to model the decreasing intensity of light as one goes to greater depths in water. There are many other contexts in the real world that could be modeled using negative exponents, so this is likely a competency that gets emphasis during this concept in your child's classroom. We hope that you found this video valuable in helping you support your child in their learning about powers with integral exponents. Please check out our other titles in this series.